All right. So in this particular lecture, we look at some of phenomena which is called diffraction. So in order to cover this phenomena, let us look at something that you are very familiar with. Let's consider a slit which has got a finite width, which is A. So A is the width of the slit, and there is a bunch of rays, collimated rays, which are coming and are incident on this slit. Now, each point in the slit acts as a source for light waves. Okay, so each point in the slit that you can see over here, like they are marked as 1, 2, 3, 4, 5, they act as sources for the light waves. So there is a bunch of parallel light beam which are incident on a slit which has got a finite width A, and each point in the slit acts as a source of secondary wave, and these different light waves therefore interfere. And this is a narrow slit, but it has got a finite width. So this is the first premise that one should understand, that there is some parallel beam of light, or parallel rays of light which are incident on the slit, and each point in the slit acts as a source of the light wave, and these light waves therefore starts to interact with each other or interfere with each other. Okay, so what happens is that if you imagine, let us imagine that you have divided the slit into half, which is total width was A, so half width was A by 2 by A by 2. Now let us take a look at the wave which is marked in blue, which is marked as 1. Okay, so this wave, okay, travels further than the wave 3, right? Just because if you drop a perpendicular from here, this particular small distance, which is nothing but A by 2 sine theta, theta being the angle, okay? So if you look at these two beams, or these two light rays 1 and 3, you will see that one has traveled a distance more than the ray 3, and that more is nothing but A by 2 into sine theta. All right. Same is valid if you look at wave 2 or ray 2 and 4. Okay. So it is the same thing. They travel by that same small distance. Okay. So this path difference, which is nothing but A by 2 sine theta, okay, if this path difference equals lambda by 2, okay, equals lambda by 2, where lambda is nothing but the wavelength of the incoming beam, then these two wave pairs cancel each other and you get what we call a destructive interference, right? So for this destructive interference to happen, your A by 2 sine theta should be equal to lambda by 2, okay, the half the wavelength. So you understood that initially the waves were all nice and horizontal, now they are deflected, okay, and that deflection angle is kind of theta. Now if the slit has got a width of A with A by 2, then the ray which is at the center travels a little bit of a lower distance than the ray at the extreme end, right? So the extreme end, this particular ray travels a little bit more distance than the central ray. So this is the central ray which is deflected. This is the edge ray which is also deflected. So this edge ray reaches the imaging plane, okay, after and travels actually effectively a larger distance, and that larger distance is nothing but A by 2 sine theta, whereas the ray at the central or the optical axis actually travels a smaller distance, which is given by the path of this ray 3. So if this path difference actually equals lambda by 2, then the waves actually destruct each other, or they cancel each other, what we call destructive interference, and the equation is nothing but A by 2 sine theta must be equal to lambda by 2. So this is the premise. Okay, so all rays from the slit are converging at a point P, and at a point P very far to the right and out of the picture. Now, for destructive interference, therefore, we already saw that it's a by 2 sine theta is equal to lambda by 2. So therefore, it's a sine theta is equal to lambda, or sine theta is equal to lambda by a. Now, instead of 2 parts, now if we divide the slit into 4 equal parts, right? 4 equal parts. Then the interference will happen, or destructive interference will happen, when sine theta is equal to 2 lambda by a, right? Because now we have divided it into 4 parts. If you divide it into 6 equal parts, the destructive interference will occur when sine theta is equal to 3 lambda by a. So you can understand, so what we did in this particular case, we divided it into 2 parts. So therefore the difference was a by 2 sine theta. Now if we divide it into 4 parts, so you can imagine that this will become like a by 4, and as a result of that you will get sine theta is equal to 2 lambda by a, and if you divide it into 6 parts, then it will become sine theta is equal to 3 lambda by a. Okay, so this is the criteria for destructive interference. Okay, so we showed it for 2. Now we are claiming that 4 will be like this, 6 will be like this. In general, the destructive interference occurs when a sine theta is equal to m lambda. M being 1, 2, 3, 4, 5, 6. Okay, so this gives the positions for the dark fringes. For the dark fringes. So it will only occur when this relationship is valid. So therefore, this gives a position for the dark fringes. There is no dark fringe for m equal to 0. Okay, so the bright fringes are approximately halfway in between the dark fringes, right? So the dark fringes formula is therefore quite easy. As you can see that if 4 gives to 2, so this is what you would actually get. A sine theta is equal to m lambda. M equal to 1, 2, 3, 4, 5, 6, right? Okay, so this gives the position for the dark fringes. Remember, dark fringes, and there is no dark fringe for m equal to 0, right? Now, when theta is equal to small, okay, theta is equal to small, okay, then it is valid to use the expression which is sine theta is equal to approximately equal to theta. So theta is in radians, remember, okay. So this theta is effectively small. So if you plot the percentage error with the degrees, you will find that up to 10, this error is very minimal, but it also is about 4 to 5% for an angle of 30 degrees. So even for large angles, this approximation, which is sine theta is almost equal to theta, is kind of not a bad approximation at all. Okay, so this is the primary thing that we want to know. Okay, now in the single slit diffraction intensity, okay, if we look at this, this is the general features of the distribution. Okay, so this is the viewing screen. This is the screen is at a distance of L from the slit. The slit has got a width of A, and this is the angle. So you can see that at sine theta is equal to 0, which is this particular stuff, the central beam, you get the maxima, okay, and most of the intensity is at the maxima, which is given by this, and it is twice the width of all the other maximas that you see, and progressively the the other fringes lie at, these are basically the destructive fringe locations, as we saw already. This was at sine theta equals to lambda by a, sine theta is equal to 2 lambda by a. This is something that we already did earlier, right? So these are the locations of the destructive fringes. Y equal to 0, which is basically this, is basically sine theta is equal to 0. Here we get the maxima, okay, and these are the corresponding minimas. And the maxima, the central maxima, is actually the most intense, and it is twice the width of the secondary maxima. Secondary maximas are these, the tails, the wings, so to say, okay, and these are the locations of the dark fringes that we can see over here. These are the locations where the brightness is, or the intensity is almost equal to 0, right? So the starting equations for a single slit intensity is, if you talk about beta, is equal to 2 pi lambda into sine theta, 2 pi lambda A into sine theta. And I, which is the intensity, is the incoming intensity multiplied by this particular factor. So as you can see that with sine theta is equal to 0, okay, so that means beta becomes equal to 0. Okay, so in other words, this particular intensity goes to a maximum. All right. All right. So you can see that, so these are, so the maximum intensity happens at the center location, and the intensity drops after, progressively at higher and higher values of your theta at different angles. So this angle, for example, will have a different intensity compared to this angle, and those are all noted over here, and those intensity profiles are given like this. So as you can see that from 0 onwards, for small angles, I mean, as you go on increasing the angle, this intensity compared to the central intensity will go on decreasing. This will go on decreasing, okay, in a certain way. So that is the starting equations for a single slit intensity profile. Okay, so this is what you get. This is how the profiles actually look like, and this is the equations that correspondingly link the profiles. Okay, now that we know what a diffraction is all about, and the fact that diffraction to a slit will actually form this bright bands and this dark bands, and the central band will be quite, intense, so to say. Now, if we do the same thing, now if we look at an imaging perspective, so this is the light with an intensity with a wavelength of lambda, which is impinging on an aperture, which has got again size which is A. Okay, and there is an image plane which is behind. Okay, so the main peak diameter, or the Q1, that you are going to record on the imaging plane. So this can be a aperture, it can be also a small particle also, doesn't really matter. It can be a particle as well. Okay? So what you can see is that it can be a slit, particle, hole, whatever it is you can think about it. So the main peak diameter, which is Q1, that you see over here in this image, you look at this image, okay, imaging, that is equal to 1.22 into r lambda divided by 2a. So what is r lambda divided by 2a? So r is, so if you look at it very, very carefully, okay, if r is equal to the focal length, then of course this becomes lambda by the numerical aperture, where numerical aperture is 2a by f, or 1 over the f number. Okay, so lambda is a wavelength, a is the size of the object, or in this case the size of the hole, whatever you call it. Okay, and r is basically the distance that the screen is from the source. So this is the screen where you are putting in the imaging screen. So and if you put it at the focal length, this will be just the numerical aperture. This will be just lambda by the numerical aperture. Okay, if you put it at the focal length. All right, if you put it at that particular focal length. Okay, so now you can see that you are not essentially, imaging, you are imaging something which is Q1 in this particular case. Okay, and the other things that you see this interference bands same way. So this is, for example, for a large particle, this is for a small particle. You see this, interference bands, which is nothing but what is called an airy disk. Okay, this happens because of the diffraction. So the diffraction leads to the formation of these airy disks, which are formed around this particle, right? So this is an important thing that one should recognize in this particular thing, that if you are imaging, you're trying to image this object, okay, what you are getting is something like a Q1, okay, which is not exactly the object, and you get this interference bands, which comes directly as a consequence of this, right? Because of the interference of cross-talking of these rays. one that we talked about, okay? Because of the destructive interference and constructive beams, right? So now, if now look at a situation like this, that a particle diameter in the object plane, say is dp, okay? So this is basically the object plane, for example, okay? So as we said earlier, this can be your lens, it can be an object, it can be anything, right? So all these things is something that you should know. Okay. So what happens, there is a particle of particle diameter in the object plane is actually dp. This is basically the, for example, a light sheet. This is a flow direction. This is what people use normally in particle image velocimetry. So f number is the focal length divided by the aperture diameter, which is already we know. So this is the focal length of the lens, and then you are dividing it by the aperture diameter, okay? Or the diameter of the particle. So the particle diameter in the object plane, say, is dp, and the magnification is basically small big z naught divided by this small z naught. This is the magnification. So from this information, the size of the particle image in the image plane is given by this particular expression. In this particular expression, you see two interesting things. There is a term called ds squared, and then there is a term which includes the magnification of the actual particle diameter. So the actual particle diameter square multiplied by mt square, which is the transverse magnification, which we already did, okay? And plus the ds square whole square root is what is imaged on the image plane. Now, in the absence of ds, recall that this mt and dp, the di would have been mt into dp. In other words, that the imaged particle diameter would be just the magnification factor multiplied by the actual particle diameter. So that would have been rather easy. You could have just divided one by the other, and you would have got the answer. Okay, that is what would have happened. But in this case, what you have is something even more significant. That is, you have this ds square, okay, plus this term which you are familiar with already. So what is this ds square? So this ds square is also called what we call the diffraction limited spot. Diffraction limited spot diameter. Okay, and mtdp is the geometric image diameter. So this is the diffraction limited spot diameter, which is nothing but 2.44 into 1 plus the transverse magnification multiplied by the f number into lambda. Okay, into lambda. Now this ds, now you should recognize this factor now enters into your equation, and this is the diffraction limited spot. So you need to know this to actually calculate what will be the diameter of the imaged droplet and what will be the actual diameter. Actually find out what will be the actual diameter of the particle in question, if that is the objective. Now for a point object or a distant object where dp is almost equal to 0 and mt goes to 0, okay, so in that particular case, that means when the transverse magnification goes to 0, or it is a point object, that means this diameter has shrunk to 0, the dp diameter has shrunk to 0, even then, okay, you have the ds. That means no matter what lens you use, what kind of sophistication you use, after a certain point, your diameter doesn't go down anymore. So whatever is your diameter of the actual particle, as it gets smaller and smaller and smaller, you get a response in the image screen. That is what you would expect. But after some time, you stop getting any response on the image screen at all, because your diameter now becomes equal to the diffraction limited spot size. As a result of that, whatever you do, you still get a fixed diameter on your image plane. You cannot reduce that. So that is a point of concern, because this is what is the diffraction limited spot is. So after a certain point, you cannot reduce the diameter of the object any further, just because of the fact that you have the spot, which is no longer dependent on your original particle diameter at all. The imaging, whatever you are imaging, that is no longer now dependent only on your particle diameter. It is just given by your diffraction limited spot. So after some time, you will still get a spot, but this spot does not correspond to any actual particle size. It is the diffraction limited spot. I think this part one needs to be absolutely clear about. So as we understood that now, therefore, diffraction can happen when you actually have a slit, hole, small objects in the path of a light beam. And as a result of that, what happens is that, you get this interference patterns. And as you know, there is a central maxima with progressively, less bright minima, less bright maxima, secondary maxima, and punctuated by this minima. Okay, all right. So that is a rather important thing that you should remember, that, this is what happens when you actually have diffraction. Now, couple of points to mention about diffraction are that, like, it's basically bending of light at the corner of an obstacle. Okay, and diffractions can be of two types also. Okay, the first type will be Fresnel diffraction, in which, if you recall, that the distance of the screen from the aperture is finite, but it could be also, Fraunhofer diffraction, where the distance of the screen from the aperture is basically infinite. All right. So Fraunhofer and Fresnel. So these are the two types of diffractions, and can happen over small objects and stuff like that. Okay. So this is an important thing to note about some small things about diffractions in general. So another feature about diffraction that you should note is that 4 points basically. The wavelength does not change in the diffracted wave after diffraction. The frequency does not change, and the speed of the diffracted wave does not change, but the amplitude of the wave decreases after diffraction. So these are the 4 points: that wavelength does not change, frequency does not change, the frequency of the speed of the diffracted wave does not change, the amplitude of the wave decreases after the diffraction over. Also, one should note a very important stuff over here, because this is just like some fine prints about diffraction, which you already know, and we have covered quite a bit in this particular lecture, is that shorter wavelength, if the wavelength is shorter, the wave spreads after diffraction to a smaller area. If the wavelength is longer, that is longer wavelength, the wave spreads to a wider area for the same slit size or same particle size, okay, or same obstacle size, so to say. So shorter wavelengths after diffraction spreads to a smaller area. Longer wavelength after diffraction spreads to a wider area. Okay, so this is also, so diffraction is affected therefore by the wavelength. Longer the wavelength, greater is the effect of diffraction. All right. So the other, so this is an important thing that you should, remember, because we deal with lasers and light sources of different wavelengths to begin with. So this is an important part, that the longer wavelengths diffract, the greater is the effect of diffraction. So now comes the opening. So if your opening is large, that is bigger the opening, the wave spreads to a smaller area. And smaller the opening, that is smaller the slit size, the wave spreads to a wider area. Okay, so in other words, the diffraction is affected by the size of the opening. Smaller the size of the opening, greater the effect of diffraction. Smaller the size of the opening, smaller. So smaller is the obstacle, greater is the effect of diffraction. Okay, so that's why you cannot go down to very small particle size because of this. More is the effect of diffraction. Okay, so these are some of the fine points that one should remember when we actually do this diffraction. We have one more point over here which we should consider. These are called diffraction gratings. So diffraction gratings are basically consists of large number of equally spaced parallel slits, as you can see over here. So this is again a parallel beam of rays that is coming and impinging on this array of slits. So these slits are separated by distances which are given as d, okay, and they impinge on it, and then therefore they are diffracted, okay, or bending of light at certain angles. So the path difference between rays from any adjacent slits, okay, this and this, for example, these 2 points, the path difference is given by delta, which is d sine theta, as you can understand. So this delta is equal to some integer multiple of the wavelengths. Then all the waves from all the slits will arrive in phase at a point on the distant screen. So you understand this point very carefully. So this is a large number of slits, can be 10,000 to 15,000 slits per inch, not per square inch, per inch. So you have this ray of lights which are coming and impinging. So the light that is going from here to here and the light that is going from here to here, they have a path difference, which is given as delta is equal to d sine theta. Okay. Now, if this delta is equal to some integer multiple of the wavelength, okay, from all the slits, then waves from all the slits will arrive in phase at a point on a distant screen. So therefore, the interference maxima will occur for d sine theta is equal to m lambda, where m is equal to 1, 2, 3. You understand? This is how you can fine tune the grating. Okay, this is called diffraction grating, basically. Okay, all right. So the diffraction grating intensity distribution is given as d sine theta is equal to m lambda, assuming that this is an integer multiple, as we said already, that this delta is an integer multiple, some integer multiple of the wavelength. Okay. So what happens here, that these are the intensity peaks. So these intensity maxima are brighter and sharper than for two slit cases. So these are very sharp peaks that you get as your interference, as interference maxima. Okay, so this is how diffraction grating is arranged. This is used for spectroscopic measurements, very routinely used for many things. But this is something that you will see even in spectrometers. They have this diffraction grating, and we already talked about a little bit of a diffraction grating. Need not be created with slits. They can be also created by other types of ways as well. But this is the most common thing, and these are very small. These spacings are very small. As I said, 10,000 gratings per inch, which is a fairly large number, so to say. Okay, so in the next class, we will now look at optical aberrations now that we have completed diffraction. And next class, we are going to do optical aberrations.